So hello everyone, good evening. I think my voice is audible now, clear. Okay, so this is lecture number 5 of linear algebra. So if you haven't watched lecture number 1 to lecture number 4, I kindly recommend you to watch all those videos, right? Then only you will have some continuation. So since there is some break between lecture 4 and lecture 5, so what I thought is first I'll revise first I'll just recall all those concepts that we have seen in lecture number 1 to lecture number 4. Then we will do this lecture number 5. So lecture number 5 is very short only. So it's a very basic concept called linear span and linear combination. That is very basic idea only. So we can finish that topic very easily. So first what I want to do is I want to recall and revise what we have seen in the previous 4 classes. Right? So I think my voice is audible now, right? My voice is audible and video is clear. So I think my voice will be audible now. So you can see if you have okay. So this is lecture number 5 of linear algebra. So if you just go to our YouTube channel and if you go to the live classes, you can see lecture number 1, 2, 3, 4. I've already completed. This is lecture number 5. So first, what we have seen in lecture number 1 is we have in the lecture number 1 we have seen what is meant by vector space and what is meant by we have seen so many examples for vector space and then we have seen some problems based on vector space. And then in lecture number 2, we have introduced what is subspace. And then in lecture number 3, we have introduced rank and a system of equations. And in lecture number 4, we have solved problems based on system of equations. It is very important concept, system of equations, right? Why I introduced this? Because everything has some meaning, right? So you will understand why I introduced the system of equations at very early, right? Some will introduce system of equations very late, but my way of thinking is different. So in the very first lecture, what we have seen is so we will just recall all the notes. Yes. So in lecture number 1, we have introduced what is vector space, right? So I'm just recalling you and brushing up all the things you have seen so far. In the very first class, we have discussed about the syllabus, and then we have defined group first. To define vector space, first we need to know the ideas of groups, rings, fields. So in the very first class, we have defined what is group. Let G be a non-empty set. A binary operation star on G is said to form a group. If G star is said to satisfy these 4 conditions, that is, it has to be closed, associative, and then there should be an identity element, and for every element, they should have inverse like that. After that, we have seen many examples whether which number system forms a group with respect to the operation plus and multiplication. And then we have defined what is field. Uh, and then we have defined what is field. So we have extended the idea of field group. Group is with single operation, and rings fields are 2 operations at a time on a single set. So and then we have defined vector space, right? So we have a non-empty set B, and then we have a field. So we have 2 things now. I'm just recalling all, right? So if you haven't watched, I recommend you to watch all those videos and then come back to this. So we have 2 sets. One is B, another is field. This B can be anything, but it has to be an abelian group with respect to addition. So let B be any non-empty set and F be any field. Then I'm going to combine B and F. B is said to be a vector space over a field F. This B has to be an abelian group with respect to addition, and together they also satisfy these 2, 3, 4, 5 conditions, okay, together. So I'm just linking these 2 sets. So if this happens, then we say that this B over a field is a vector space. And then we have seen many examples for vector space. So Rn of F, Rn B is your Rn, and F is any field. So majority in UPSC point of view, we will always have only 2 field, one real number, other is complex number. So Rn of F is a vector space. So we have proved that this is a vector space. Is Rn, that is n tuple. and your field is, it can be anything. And then we have shown set of all polynomials over a real number is a vector space with usual addition and scalar multiplication over polynomial. That is, your V is your polynomials, and phi and f is a real number. And then we have the set of all functions, also a vector space over a real number. And then set of all m by n matrices over real number is also a vector space. And then we have seen some problems, right? They will give some operations. With that operations, whether that B forms a vector space or not over a field F. Those are the problems that we have seen in the first three classes, first three problems. And then in lecture number 2, we have defined a subspace. So we have a vector space. That means we have a set B, and then we have a field F. This V has to be an abelian group with respect to addition, and together V and F should satisfy the other four conditions. Now you take a subset. You take a subset W of V. As of now, I'm saying only subset. You know what is subset, right? You take a subset W of V, then the subset will be a subspace if it satisfies these two conditions. Very, very important. You take two elements, you take two elements U, V in W, and you take some scalars in the field here. You take two element U, V in W, then the sum U plus V should also be in W, and you take some element alpha in the field F, then alpha U should also be in W. So these two conditions can be uh, linked, and it can be said in one condition, that you take two element alpha beta in F, you take UV in V, then alpha U plus beta V has to be in W. Very, very, very important, right? So don't think I'm just reading, right? I already explained all in lecture 1 to lecture number 1, 2, 3, 4, right? So if you haven't watched, go through that. Just touching up, if I already seen, I'm just recalling all. So you take UV in W, then the sum should be also be in W. You take alpha in field F, then alpha U should be in W. These two can be together proven as one condition, that if you want to prove something to be a vector space, you take two elements UV in W and alpha beta in F, then you show that alpha U plus beta V. This clear combination is also in. And then we have seen some problems whether it is a subspace or not. We have seen many problems. And in lecture number 3 and lecture number 4, we have, these are very easy, right? Rank of a matrix we have seen, and then how to solve a homogeneous system of linear equations, and how to solve a non-homogeneous system of linear, right? So I strongly recommend you to watch these 4 videos. So without watching these 4 videos, don't continue lectures, right? Yes. um, this video, in this class, we're going to see linear span and linear combination. These are very basic ideas only. I'll try to complete within 15 minutes to 1 hour. I'll try to complete this stuff. And from next class, very, very important, we are getting into the core. We'll be starting linear dependent, linear independent, basis, dimension, and then we have seen we will do many problems based on finding dimension, right? Okay, so we will start with linear combinations and linear and right. Okay, so we'll start with linear combinations and linear. So linear combinations and linear. Linear combination and a linear. So first, what I will do is we will start with some examples, right? We will start with some examples. Then we will extend our idea. Then we will extend our idea. So I'm going to take a vector space, right? So consider a vector space over P of F, right? This is a way to represent a vector space, right? Consider a vector space. Let us take a vector space to be R2 of R, right? That is, your V is your R2 and the field is R. So I'm taking consider a vector space R2 of R, right? So I'm taking a vector space up to R2 of R. So first, I will start with some examples, right? Consider a vector space R2 of R. So that is, your V is your R2 and your field is real number, right? And you know your V is your R2, and R2 is nothing but a two-dimensional space. It consists of all two tuples. So it consists of all those x comma y, and this x comma y both belongs to real number. This is the R2. Every pair, every element will be a ordered pair, right? X comma y, and this x comma y belongs to R, and the field is your real number. Now let us take two elements uv in the V, right? So let us take u comma v belongs to V. Just for understanding, what I will do is, let us take u to be some 1 comma 2, and let us take v to be some 3 comma 4. You can take any. I'm just giving you some more motivation towards linear span and linear span and linear combination. I'm just taking two elements. I'm just taking two elements in V, and V is your R2. And let us take two elements alpha beta in the field, right? Let us take two elements alpha beta in the field. In this example, I have taken u to be 1 comma 2, v to be 3 comma 4, and alpha beta is in the field. So let us take alpha to be equal to 1, beta to be equal to 2. Now what I'm going to do is, I'm going to form a new combination, right? I'm going to form a new combination. I'm going to call a new vector alpha u plus beta v. This is a new vector, right? Alpha u plus beta v. So you can see alpha u into beta v. So I have taken alpha to be equal to 1, and u to be equal to 1 comma 2, and beta to be equal to 2, v to be equal to 3 comma 4. Now you can see this will be 1 comma 2 plus 6 comma 8. This is 7 comma 10. And you can see this also belongs to B, right? Because your B is your R2. So what I did is, I've taken two element UV in V, and I've taken two elements alpha beta in the field F. Now I have formed a new vector. I have formed a new vector alpha u plus beta v. So if I have I've taken two vectors, you can similarly take three vectors, and then you can find all possible combinations. This is one linear combination of these two vector. Yes or no? This is this is one one linear combination. This is one linear combination of u and v. See, I have taken alpha to be equal to 1, beta to be equal to 2. Alpha beta belongs to the field. This is a real number. So for this single vector, for the single UV, you can express this in infinitely many combinations, right? If you vary alpha and beta, you will get different combinations. So this 7 comma 10, 7 comma 10 is a linear combination of 7 comma 10 is a linear combination of u and v. Yes or no? Because if I say something is a linear combination, this 7 comma 10 can be expressed as some alpha times u, some alpha times u plus beta times v. So if I have two vectors, then I can generate infinitely many vectors by linear combination of those two. How? Alpha u plus beta v. See, I have taken alpha to be equal to 1, beta to be equal to 2. So this is 7 comma 10 is one linear combination of uv. Similarly, if I take another alpha and another beta, let us take alpha to be equal to 2, beta to be minus, then you will have another linear combination of this uv, right? So we say each is a linear combination. 7 comma 10 is a linear combination of uv. And similarly, if you take alpha to be equal to 2, beta to be equal to minus 1, so what you will have another linear combination, right? So alpha is 2, and your u is 1 comma 2, and your beta is minus 1, and your b is 3 comma 4. This is 2 comma 4 plus minus 3 comma minus 4. So 2 minus 3 is minus 1, 4 minus 4 is 0. Again, you can see this 1 minus 1 comma 0 is a linear combination of u and v. So we call each of this a linear combination. Now this u comma v can be expressed as infinitely many linear combinations. Yes or no? If I vary alpha and beta, then there are infinitely many linear combination for this UV. It is obvious, right? Because alpha beta belongs to real number. Real number is infinite. So this single UV, let us take S to be equal to, let us take B to be equal to the same example R2, and let us take S to be a subset of V. Let us take S to be a subset of V. Let B is equal to R2. Let us take S to be a subset of V. Let S be a let S be a subset of V. Then what is S? In this example, our S is 1, comma 2, 1, 3, comma 4. Our S is 1, comma 2, 1, 3, comma 4. Now you collect all those linear combinations. 7, comma 10 is one linear combination. If I take alpha to be equal to 1, beta to be equal to 2. And similarly, minus 1, comma 0 is one linear combination of that UV. If I take alpha to be equal to 2, beta to be equal to minus 1. If I vary alpha, beta, I will get infinitely many linear combination for that UV. Right, this is our U, this is our V. This is our U, this is our V. Now, you collect all those linear combination, alpha U plus beta V, and this alpha beta belongs to field F. This consists of all those linear combination of UV. All those linear combination of UV called the linear span of S, right? So linear combination is one combination of that UV. You collect all those possible combination and put it in one set. That set is called linear span. We're going to call as linear span, right? This is example. Now we're going to define what is linear combination and linear span. So linear combination is you take UV, you have some vectors, you make some combination with the scalars. Then every combination is a linear combination. You collect for that UV, you collect all those linear combination and put it in one set. That is called linear span of that subset, right? So we will define what is linear combination and then we will define what is a linear span. So linear combination. So linear combination. So we'll define what is a linear combination and then define. So P of F, let P of F be a vector space. Let V of F be a vector space. So you have V and then you have a field F. It can be anything. In the previous example, I have taken V to be equal to R2, F to be equal to R. So let V of F be a vector space. Let us take some vectors V1, V2, V3, V4, and so on up to Vn belongs to V. In the previous example, I have taken only two vectors UV. They will generalize V1, V2, V3, and so on up to Vn. Right? Each of them is a vector. Each of them belongs to V. Then um, a linear combination. A linear combination. A linear combination is expressed as a linear combination is expressed as here you have some alpha 1, alpha 2, and so on up to alpha n. Then the linear combination is expressed as alpha 1 v1, alpha 2 v2 plus alpha 3 v3 and so on up to alpha n vn. Now it is clear, right? In the previous example, this is one linear combination. If you vary alpha 1, alpha 2 is called a linear combination, right? Now we will define what is a linear span, right? Now we will define what is linear span. Again, let V of f be a vector space. Let let V of f be a let V of f be a vector space, and S be let S be any non-empty let S be any non-empty subset of V. So we have a non-empty subset of V. Then uh, the set of all let S be any non-empty subset of V. Then the set of all linear combination the set of all linear combinations linear combinations of elements of S is a linear span of S denoted by L of S. Now it will be very easy for you to understand, right? You collect all those linear combination of that S, then that is a linear span of S, right? So that is, you take a non-empty set S, V1, V2, and so on up to Vn. You collect all those linear combinations. This is one linear combination. Collect all those linear combinations, put it in one set, right? Uh, alpha I V1, alpha I V2, and so on up to alpha I Vn. And this alpha I belongs to the field. The set of all linear combination, right? Set of all linear combinations of elements of S is the linear span of S. Is it clear, right? Those two definitions. So you just you will start with the examples and then we have defined, right? I'm taking UV. Then for every alpha beta, you will have each of them is called linear combination. You collect all those linear combination, put it in one set for that S. Then see, first you need to fix S, right? And then you have to perform all the linear combination. So S has to be a subset of V also. It has to be a subset of V also, right? Okay. So we have defined linear span now. Now the next thing what I'm going to do is we're going to do three problems based on a linear span, right? So problem one. Problem one is find the linear span. Find the linear span of subset S, which is 1, comma 0, comma 0, 0, comma 1, comma 0 of R3 of R. See, we have R3 of R, right? So you have a vector space R3 of R, and I have a R3 of R means what? This is your V is your R3, and your field is real number, right? So V consists of R3, and you can see S is a subset of V, right? This is a subset of V, right? Because 1, comma 0, comma 0, 0, comma 1, comma both are uh, both are in okay. Okay, just a minute. Okay, so find the linear span. So I've taken S, which is subset of R3, right? Yes. Now I'm going to find linear span of S. So S is 1, comma 0, comma 0, and 0, comma 1, comma 0. Now we need to find linear span of S. What is linear span of S? Set of all combinations of these. That is a linear span, right? So linear span of S is alpha times 1, comma 0, comma 0 plus beta times 0, comma 1, comma 0, right? Alpha beta belongs to field F. So this consists of alpha comma 0 comma 0 plus 0 comma beta comma 0. Now when you add this, you will have alpha comma beta comma 0. All the linear combinations of this is a linear span. This is set of all linear combination. This alpha beta belongs to the field F. Now you can see that this spans R2, right? This spans R2 because you can see third quadrant is 0 for this. So this will span R2. It will generate entire points in R2. These two vectors. Set of all linear combination will give you all the vectors in R2. Okay, so problem 2. Problem 2 is find the span. Find the span of the subset S. So which is 1, comma 2 and 0, comma 2 of R2 of R. So we need to find all the linear combination and put it in one side, that is a linear span. So find the span of the subset S, which is 1, comma 2 and 0, comma 2 of R2 of R, and verify whether 3, comma 7 belongs to span or not. So we need to verify whether this is the span or not, right? Whether this 3, comma 7 can be expressed as a linear combination of these two. If this 3, comma 7 can be expressed as a linear combination of these two, then we can say that 3, comma 7 will be in the span, right? Okay, first we need to find L of S. So what is L of S? Alpha into 1 comma 2 plus beta times 0 comma 2. So this is a linear span, right? Alpha comma beta belongs to the field. Here field is real number. So this is alpha to alpha, 0 to beta. Alpha comma beta belongs to real number. So this is nothing but alpha comma 2 alpha plus 2 beta. Alpha beta belongs to the field here. This is the set of all linear combinations of S, which is called as linear span. Now we need to verify whether this 3 comma 7 belongs to S. Now we need to verify whether this C 3 comma 7 belongs to L of S or not. So we need to verify this. So if the 3 comma 7 can be expressed as a linear combination of these two vectors 1 comma 2 plus beta times 0 comma 2, if there is some alpha beta, if there is some alpha beta in the field real number, if there is some alpha beta such that this linear combination makes this as 3 comma 7, then I can say 3 comma 7 belongs to L of S. L of S consists of all linear combination, right? If there is some, they are asking that whether is there any alpha beta such that these two sum will give us 3 comma 7. So let us try to find alpha and beta, whether we will check whether it is possible or not. So here we have alpha plus 0 beta is equal to 3, and we have 2 alpha, 2 alpha plus 2 beta is equal to 7, right? I'm just see, these are very basic, right? So two tuples are equal, corresponding coordinates are equal. This implies alpha is equal to 3, and 2 times alpha is 3, 6 plus 2 beta is equal to 7, 2 beta is equal to 1, so beta is equal to 1 by 2. See, we have found alpha and beta such that alpha into 1 comma 2 plus beta into 0 comma 2 gives us 3 comma 7. So that means what? 3 comma 7 can be expressed as a linear combination of these two. That means 3 comma 7 will be the linear span of S. The linear span is set of all linear combination of UV. So set of all linear combination will have 3 comma 7 also, because there exists some alpha beta such that the linear combination of these two give 3 comma 7. You can check this. Just put 3 here, you just put 1 by 2 here. So 3 into 1 plus 1 by 2 into 0, which is 3. Now 3 into 2 is 6. 6 plus 1 by 2 into 2. So which is 6 plus 1, which is gives us 7. So that means there exists alpha beta belongs to real number such that 3 comma 7 can be expressed as alpha times 1 comma 2 plus beta times 0 comma 2. Implies 3 comma 7 belongs to L of S. Implies 3 comma 7 belongs to L of S. Right? Okay. Now we'll move on to problem number 3. Problem 3 is find the span, find the linear span, find the span, find the span of subset S. Find the span of the subset S. So which is 1 comma 2 1, 2 comma 4 of R2 of R2 of R, and verify whether 3 comma 7 is in span or not. Right? Now we will see whether first we will try to find all the linear combination of this, which will give us linear span. So linear span of S, L of S is alpha times 1 comma 2 plus beta times 2 comma 4. Right? So this alpha beta belongs to real number, which is the field. So this gives alpha plus 2 beta comma 2 alpha plus 4 beta. Alpha comma beta belongs to real number. Right? I'm just multiplying alpha inside and then I'm adding the coordinates. So this is a linear span of S. Now we need to check whether 3 comma 7 is in the span or not. Right? We need to check whether 3 comma 7 is in the span or not. Okay. So we need to check whether 3 comma 7 is in L of S or not, right? So if 3 comma 7 can be expressed as a linear combination of these two vectors, which is 1 comma 2 plus beta times 2 comma 4, then I can say this will be in L of S. This implies alpha plus 2 beta equal to 3, and we have 2 alpha plus 4 beta is equal to 7. See, this implies alpha plus beta is equal to 3. Alpha plus beta is equal to 3. Now, if I take 2 outside here, we will have alpha plus 2 beta is equal to 7 by 2, right? Just take 2 outside, alpha plus 2 beta, and then bring 2 here. Now, you can see this contradicts, right? This contradicts, right? The same alpha comma beta contradicts. A same alpha comma beta cannot satisfy this simultaneously, right? Alpha plus 2 beta has to be 3, and alpha plus 2 beta has to be equal to 7 by 2. This implies what? This has no solution, right? Has no solution. Has no solution. You can also do this by consistency also. This implies there is no alpha comma beta. That means what? This implies the vector 3 comma 7 doesn't belongs to L of S. So there is you vary alpha beta, but you will not get 3 comma 7 even if you put any alpha comma beta. Right? Okay, so we're going to prove a theorem that the set of all linear span is a subspace, right? Theorem 1. The linear span, the linear span, the linear span L of S for any subset, linear span L of S for any subset S is a subspace, is a subspace of V of F, right? We're going to prove that the linear span is a subspace of V of F. Okay, so what I'm going to do is we have V, and then we have field, right? And then we have field. So this V of F is a vector space. That means this V has to be an abelian group with respect to addition. V and F together will satisfy some four conditions. Now you take S, right, which is a subset of V. Then you form L of S. Then you form L of S. Now then you form L of S, right? L of S is set of all linear combinations of S, right? Here you have alpha 1, alpha 2, and so on up to alpha n. Now we're going to show that this L of S is a subspace. This L of S is a subspace. Here your W is L of S, right? You know how to prove a subspace, right? See, W is a subspace by definition. We already seen the definition of subspace, right? Let me recall that again and just show you that. The lecture number 2, we have defined what is subspace, right? You can see that the W is a subspace. Where it is, yes. So if I want to prove W is a subspace, you take two elements UV in W, then you show that alpha U plus beta V is also in W. Here our W is L of S, right? Your W is our L of S. So when you take two elements in W, then you show that alpha U plus beta V is in W. Now here our W is what? L of S, right? This is our W. That means you take two elements. UV in L of S. Then you show that alpha U plus beta V is also in L of S. Then this will be a subspace. Yes or no? The definition of subspace. This is our W now. You take two elements in L of S. Then you show that alpha U plus beta V. You take two elements here. Then you show that this also belongs to L of S. Then I can say it is a subspace, right? Solution. Proof. Okay. Now let V of F be a vector space. Let V of F be a vector space, and S be any non-empty subset. S be any non-empty subset. Let us take S to be some what I can say. See, S consists of all those linear combinations of S, right? Let us take S to be some V1, V2, V3, and so on up to Vn, right? These are all some vectors in these are all X, S. Now you take two element in. Now you form L of S. Now what is L of S? It consists of all those linear combinations: alpha 1 V1, alpha 2 V2, and so on up to alpha n Vn. This is our L of S. Now you take two elements in L of S. Let u comma v belongs to L of S. Now we need to prove that what we need to prove. What I need to prove, alpha u plus beta v is also in L of S, right? UV belongs to L of S. That means u will be an element of this form because u belongs to L of S and every element in L of S is a linear combination. Let us take u to be some alpha 1 dash v1 dash, alpha 2 dash v2 dash, and so on up to alpha n dash v1 dash vn dash vn dash, right? See, these alpha 1 dash, alpha 2 dash, all are belongs to the field, and this v1 dash, v2 dash, all are belongs to that S, right? Now you take, I'm taking two element UV in L of S. I'm taking U to be this. Let us take V to be some alpha 2 dash, V2 dash, alpha. Okay, let us take this as something I need to, let's take beta 1 dash. What I can do. We have already taken V1, V2, V3. Let us take some U1, U2, U3, right? I'm just differentiating, that's it. Some beta 1, okay, let it be as it is. Some beta 1, V1 dash, some beta 2 dash, V2 dash, and so on. Beta n, beta n dash, Bn dash. This beta 1 dash, beta 2 dash, all are belongs to the field F. Now I need to prove alpha u plus beta v is also in B. Now what is alpha u plus beta v? Alpha into alpha 1 dash v1 dash, alpha 2 dash v2 dash, and so on, alpha n dash plus beta into v plus beta into v. V is beta 1 dash v1 dash, beta 2 dash v2 dash, and so on up to beta n dash v. See, I need to show that this combination is also in L of S, right? This combination is in L of S. Can I write this as alpha 1 dash plus beta 1 dash into v1 dash and alpha 2 dash beta 2 dash into v2 dash and so on up to alpha n dash n dash plus beta n dash n dash. Sir, no? See, I'm just regrouping. All are very easy only, right? Let us write this as alpha n dash beta n dash. See, can I write? I'm just write this as some scalar, right? Let us write this as p1 dash, p2 dash, and so on up to pn vn dash. See, where this p1, p2, and so on up to pn belongs to field F, right? Because you can see alpha, beta, alpha 1, beta 1 dash all are belongs to field. Since it is a field, it is closed. So therefore, this element is also will be in field. This also will be in field. Now you can see this also belongs to L of S because you can see alpha u plus beta v can also be expressed as uh, p1 v1 dash, p2 v2 dash, and so on, right? Or else let us take this as um, v1 dash, v2 dash, v3 dash, vn dash, v1 dash, v2 dash, alpha 2 v2 dash. Okay, I'm taking S, V1 dash, V2 dash, V3 dash up to Vn dash. So I'm proving that I'm taking UV. I'm taking two combinations in S. So S consists of V1. See, just for understanding, I'm just using these symbols, right? You can whatever convenient you can do that. I'm just doing this theorem in flow. That's why I'm doing some random variables. So I'm just taking a set S. You form all those linear combination. You take two element linear combination. You show that this also linear combination. Very simple, nothing to think big, right? Now we can see that. So therefore, alpha u plus beta v is also belongs to L of S, because this also we express as linear combination of these vectors v1, v2, v or some alpha or some scalars. Here scalars are these. Right? So that means L of S is a subspace. That means L of S is a subspace. Right? Okay. Now we will define what is called a linear sum of two subspace, right? Define what is linear sum of two subspace. Is it clear as of now, right? Is there any doubt up to now? Okay. So next is definition. Linear sum of subspace. Actually, already we have seen a definition of union of two subspace. Whenever you have two subspace W and W2, we have defined union of two subspace W1 union W2. Now, if I have two subspace W1 and W2, I'm going to define what is W1 plus W2. Right? So let W1 and W2 be two subspaces. Let W1, W2 be subspaces, be two subspaces of V of F. Right? Let two subspaces of V of F. Then the linear sum. Then the linear sum of the subspaces. The linear sum of the subspaces W1 and W2 denoted by W1 plus W2 is given by, I'm going to form W1 plus W2, which is W1 plus W2, right? Where this small W1 belongs to capital W1 and small W2 belongs to capital W, right? Or else you just write U plus B. If you don't want to use W and W2, you just write all those U plus B, right? Is your convenient. So you just this is nothing but all those U plus B. U belongs to W1 and this B belongs to W2, right? So that is nothing but you are summing up uh, U plus B, and this U belongs to W1 and B belongs to W2. This is completely different from union of two subspaces, right? In a union of two subspaces, we have defined what is meant by union of two subspaces, and then we have also proved that union of two subspace is not a subspace, right? Let me recall that also. So you can see after defining subspace, uh, let's set off also. Yes, I think now we have defined the union of two subspaces need not be a subspace, right? So here I've given you an example. I have taken V to be R2, set of all real numbers, two-dimensional coordinates, right? I've taken two subspaces, W1, W2. I've taken W1 to be the x-axis and W2 to be the y-axis. So I have proved that both are subspaces, right? I have proved that W1 is subspace, W2 is subspace. Now, W1 union W2. So W1 union W2 means you just have to combine. You should not add. You take this and union. I have proved that this is not a subspace. Why out to not a subspace means what is subspace? You take two elements in W, then sum has to be in W, right? But here what I'm doing is I'm taking an element P, two elements in union. Uh, I'm just recalling, right? I'm taking P to be some 2 comma 0, P 0 comma 0 comma 0 comma 3. But P plus Q can see this not belongs to W into W2, right? Because W into W2 consists of either the points in x-axis or points in y-axis. But this is not belongs to this. This is not a subspace. Here, we are unioning these two, but now we are making a sum of subspaces, right? I'm just adding both. I'm just adding both. Now I'm going to show that this is a subspace, right? Now I'm going to show that the linear sum is a subspace, right? I'm going to show that linear sum is a subspace. Theorem. Is it clear, right? Is this sum of these two subspace? That is union of these two. Theorem. If W1 and W2 are two subspace of V, are two subspace of V, then W1 plus W2 is also a subspace, right? Let me prove this very easy proof. So what I have is I have a set B and then I have a field F. I'm taking a two subspace W1 and I'm taking one more subspace W2. Now I'm going to form W1 plus W2. See, already W1 and W2 are subspace. Remember that. Already W and W2 are subspaces. Then the sum of two subspace is also subspace. Right? Okay. Now, what is W1 plus W2? So it consists of all those U plus V, such that this U belongs to W1, this V belongs to W2. Right? Okay. Now I need to take two elements here. I need to show that these two are. I need to take two elements in W1 plus W2, and I need to show linear combinations also in that set. Right? Okay. Let me show that. Let us take two elements. What I can do? Let us take some P comma Q in W1 plus W2. What I need to prove? Alpha times P, alpha times P, alpha times. I need to prove alpha times P plus beta times Q is also in W1 plus W2. This is what I need to prove, right? You just take two elements in this set. Then need to prove that this combination also W plus W. So let us take two elements. Let us take P to be some W1. See, you can take anything, right? Let us take P to be some W1 plus W2. Let us take uh, Q to be Q to be some W1 dash plus W2 dash, right? This W1 belongs to capital W1. This W2 belongs to capital W2. Here W1 dash belongs to W1. W2 dash belongs to W2. See, this P is in W1 plus W2. So first element should be in W1, second element should be in W2. Right? Okay. Uh, so now I need to show that alpha P plus beta Q is also in, it belongs to W1 plus W2. Okay, now I need to show that, now we will prove that alpha P, alpha times, will prove that alpha times P plus beta times Q. So alpha times, what is P? P is W1 plus W2 plus beta times, what is Q? W1 dash plus W2 dash. So can I write this as alpha W1 plus beta W1 dash plus alpha W2. I think everything is going smooth, right? Is there any internet issue? Okay, is there any internet issues? Is it smooth? Or is there any internet issues? I think videos bitrate is slow. Okay, I think there is some problem in the video. Just a minute, right? I'll get back. I think it is fine now. Okay, so what we'll do is we need to show that alpha p plus beta q is in alpha q plus beta p is in W, right? I think the video bitrate is getting low. Video bitrate is low. Okay, so let me continue, no problem. Okay, so we need to prove that alpha p plus beta q is also in this, right? So alpha W2 plus beta times W2 dash. Now, can I write this as alpha W1 plus alpha W1 alpha W2 plus beta W2 dash? Okay. See, now very important, right? Very important. And I see I have taken we have note, right? So very important note. So we have taken we have W1 and W1 dash belongs to W1. Yes or no? So you can see that W1 I've taken W1 and W1 dash. W1 and W1 dash both belongs to W1. W1 and W1 dash both belongs to W1. So and since W1 is subspace, can I say alpha W1 plus beta W1 dash is also in W1 because W is a subspace, right? And also we have W2 and W2 dash both belongs to W2. And can I say alpha W2 plus beta W2 dash is also in W2 because both because both W1 and W2 are subspace. Both W1 and W2 are subspace. That means this belongs to W1, right? This belongs to W1. This belongs to W2. So you can see alpha beta, alpha p. You can see that alpha p plus. I am writing always beta instead. So alpha p plus beta q belongs to W1 plus W2. This implies W1 plus W2 is a subspace. W1 plus W2 is a subspace, right? So very easy problem, very easy theorem. That see union of two subspace is not a subspace. Union of two subspace is not a subspace. Union of two subspace is not a subspace, but sum of two subspace is a subspace, right? Sum of two subspace is a subspace. Okay. I think I completed the proof. It is these two or not. Okay, see what I'll redo this, right? So I'll just read this what I did. I need to prove that the sum of two subspaces subspace, right? I've taken two W and W2. Remember, both are a subspace. W is also subspace, W is also subspace, right? So what I'm doing is I'm taking two elements. you take two elements w1 and w1 dash here. Here you take w2 and w2 dash. And since w1 w1 dash both are in w1, this implies alpha w1 plus beta w1 dash is also in w1 by definition of subspace. And w2 is also a subspace. So alpha w2 plus beta w2 dash is also in w2. So what I'm doing is you just take two elements in w1 plus w2. So I've taken p to be w1 plus w2. I've taken p to be w1 plus w2, q to be w1 dash w2 dash. And I need to prove that alpha p plus beta q is also belongs to w1 plus w2. Alpha times p plus beta times q. I'm just regrouping this. This belongs to w1, right? Because you can see alpha w1 plus beta w1 dash belongs to w1 by definition of subspace. Alpha w2 plus beta w2 dash also belongs to w2. So this belongs to w1, this belongs to w2, this belongs to w1 plus w2. Therefore, this combination belongs to this. Therefore, it is a subspace, right? Now we're going to prove the last theorem in this class. Then to wind off today's class. Theorem. So what this theorem says is let v of f let v of f let let v of f be the vector space of all. Let v of f be the vector space of all functions from r to r, from r into r. Let ve and vo let v be set of let ve denote let ve be subset of even functions and vo be the subset of odd functions, right? Prove that ve vo are subspace of B, and you also prove that ve plus vo gives B, and then prove that ve intersection v naught is empty. It contains only zero function. So we need to prove these things, right? So we need to prove three things here. See here, V consists of all those functions, right? So V consists of all those functions from real number to real number. Here we have two types of functions. One is all those even functions, and one consists of all those odd functions, right? So VE consists of all those even functions. What is even function? All those f in V such that f of minus x is same as f of x, right? Even function. And vo odd function, all those f in V such that f of minus x is minus f of x. This consists of all those odd functions. So first what I need to prove is both are subspace, right? So first we will prove that first we'll prove the first thing, that BE, set of all even functions, BE is a subspace, BE is a subspace of B. So first we will prove this, right? So how to prove subspace? You take two element in BE. So you take two element in BE. What we need to prove? Alpha F plus beta G is also belongs to B. Right? It's very simple, right? Whenever you need to prove subspace, you take two elements in W, then alpha U plus beta V is also in W. Here W is there are all even functions. So you take two element in B, you need to prove this also belongs to B. Right? Okay. Now we have F comma G belongs to V. F comma G belongs to V. So let us take let us take f of see f and g both are even functions. So f of minus x is same as f of x, and g of minus x is same as g of x. Now I need to prove alpha f plus beta g is also an even function, right? I need to prove alpha f plus beta g is also an even function. So this is, can I write this as alpha into, okay, I need to put this as even function, right? Let us find alpha f plus beta g of minus x. So can I write this as alpha into f of minus x plus beta into g of minus x. This is f of minus x is same as f of x because f g both are even function, and this again g of x. Can I write this as alpha f plus beta g of x? If you have watched lecture number 1, it will be easy for you. Now you can see that this, see, let us call this as some h, right? So let us call this as some h. So h of minus x same as h of x. That means what? This is an even function. You see this as single function, right? You see alpha f plus beta g as single function, and this single function is also an even function. This implies alpha f plus beta g, this belongs to V because this is also an even function. So that means V is a subspace of V, the subspace of V, right? Now we will prove the second thing, that of all odd functions is a VO is a subspace of V. We need to prove this. VO is a subspace of V. Now, what is VO? Set of all odd functions. This consists of all those functions in V such that f of minus x is minus f of x. Right? Now, you take two elements fg in odd function. Now, what I need to prove? Alpha f plus beta g is also an odd function. Right? Now, we'll prove this. Now, what is alpha f plus beta g of minus x? See, alpha fg belongs to v naught. Fg belongs to v naught. That means what? F of minus x is minus f of x, and g of minus x is minus g of x because fg are odd functions here. So can I write this as alpha into f of minus x, beta into g of minus x? This is minus f of x. This is minus g of x. Let us take minus outside here. Can I write this as alpha f plus beta g of x? Now we can see that this of minus x is minus of that. That means what? Alpha f plus beta g is an odd function. So that means it is a subspace. Very simple, right? So if you take two fg in even function, then alpha f plus beta g is also an even function. That means B is a subspace. And similarly, you take two odd functions, then this also an odd function. That is this linear combination function is also an odd function. That means we have proved the first part such that VE and V naught are V and V naught are subspace of V. Now we need to show that the linear sum. We need to show that. Now second thing is we need to show that VE plus V naught is belongs V. If you add all those even functions plus all those odd functions, you will get V linear sum, right? Linear sum. Uh, Now, see, whenever you need to prove equality in mathematics in theorem, you need to show that this is contained in B, this is contained in this. See, whenever you need to prove A is equal to B, you need to show A is contained in B, B is contained in A. It's a proofing technique, right? So whenever you need to show equality. So first what we'll do is, we will show that B plus B naught is contained in B and B is contained in B plus B naught, right? We will show two things. We will show two things. Okay. Since BE and V naught are subspace, PE plus V naught is also a subspace because we already proved that sum of two subspace is a subspace of V. Then V plus V naught is also a subspace of V. Right? Here V is set of all functions. This implies E plus V naught will surely contained in V. Yes or no? Very simple, right? We need to show this is contained in this and this is contained in here. This is obviously contained in V because V, E and V naught both are subspace and sum of two subspace is subspace, and this is contained in V. So this is obviously true. Now I need to prove B is contained in this, right? So that means you take an f in B, you take any function in B, then you need to express this f as a sum of even function and odd function. Then I can say any B can be expressed as this. I proved that this is contained is here. Now I need to prove you take any, this is contained in this. That means you take any element in B, you need to tell that that element can be expressed as sum of even function and odd function, right? Okay. Now I need to prove this function f can be expressed as fe plus f naught. This implies if I prove that, then I can say B is contained in B plus B naught. Is it clear? You take one arbitrary f here, then you say that this is expressed as this plus this. That means B is contained in this B plus B naught. Now we'll prove that, right? So let us define fp of x. Let us define fp of x to be 1 by 2 f of x plus f of minus x, and let us define fo of x to be 1 by 2 f of x minus f of minus x. See, this fp and f naught are even functions, right? You can easily check this, right? fp is an even function. Fe is even and fo is odd. I think you can check this, right? You can check this, right? Because if you put fp of minus x, you will get as f of x again, and if you put fo of minus x, you'll get minus f of x, right? You check this out, right? Fe is even. That is fp of minus x is same as fe of x. You can check it out, right? Uh, this is fe of x, and similarly, if this is an odd function, you can check it out that fo of minus x is minus fo of x, right? You just check it out, very easy. You just put minus x here, you will get as minus fo of x. Now what is fp of x plus fo of x? If you add this, what you will have? F2 fx plus f of minus x plus 1 by 2 fx minus f of minus x. Now when you add this, you will have what? F of x by 2 f of minus x by 2 plus f of x by 2 minus f of minus x by 2. These two will get cancelled. So you will have f of x, right? Now we can see that I have taken f in B. Then if I redefine fp and f naught as like this, then I can say that any f can be written as b plus b naught, right? B plus b naught. B is, see here I've done fp, and it's not an issue, right? And this of all those even functions. If you want, I can also change this to b plus b naught, right? These are just sign conventions, right? B plus b naught, right? B plus b naught. If I say that, then I can say b is contained in b naught. So fp of minus x, this is an even function and this is an odd function, right? Okay. So that means this is f of x, and this f of x belongs to what? B. So that means this implies B is contained in B plus B naught. I have taken an arbitrary f, then I have expressed that f as sum of even function plus odd function. This is star. So from star and double star, uh, B plus B naught is equal to B. Is it clear? This is contained in this and this is contained in this. So therefore, it is a subspace, right? I've taken an arbitrary element B. I need to show that this is B, right? I need to show that B plus B naught. If I say that, I can say I can write B is contained in B plus B naught, right? Okay, so I have defined B to be this, B naught to be this. This B is even and this B naught is odd, because you just put B of minus x, you will get this as this B of minus. See, these are sign conventions, right? You can do any symbol. P of minus x is same as b of x. Vo of minus x is minus vo of x. Right? So we have put the second part. Now, uh, see, there is no function which is even and odd. That is, the only function which is even and odd is a zero function. You cannot find a non-zero function which is both even and odd. So intersection of even function and odd function will only have zero function. You cannot find a function which is both even and odd other than zero function. That is second. That is the third thing we need to prove, right? Okay. Last part. So last part is we need to prove that the intersection contains only zero function. B intersection B naught contains only zero function. So a function which is both even and odd is zero function. Very obvious, right? See, f of minus x is equal to f of x. That means it's an even function, right? F is even. And f of minus x is minus f of x. That means f is odd. That means f is odd. So fe intersection f means, that means what? F is both even and odd. Both even and odd. That means f of minus x is same as f of x and same as f of minus x, both even and odd. If we take these two, what do you will have? F of minus x is equal to f of minus x is same as f of x, and f of x is f of minus x is minus f of x. When you solve this, what do you will have? When you solve, if you take these two, if you take these two, f of minus x, f of minus x is same as f of x, and f of minus x is same as minus f of x, right? Now I need to show that what I can do is just add or subtract. Okay, let us try to subtract these two, right? Let's try to subtract this. This is even function, this is odd function. All are equal. This is true only if f of x is 0, right? It's true only when f of x is 0. So if I subtract of x from here itself, I can say that 2 times f of x is 0, right? 2 times. Uh, okay. Let us prove this. Let us prove by this. F of minus x is f of x. That is even function. F of minus x is minus f of x. So from these two, can I say 2 times f of x is 0? Or no? So that means f of x is 0. So that means intersection contains only zero function. This means this is a zero function, right? Zero function. So that means B intersection B naught contains only zero function. Therefore, we have proved that the third theorem, third part, right? So if V of f is a vector space, V plus V naught is a subspace of V. The V plus linear sum of V plus V naught will give you V. Intersection will contains only zero. So for this, you show that this is contained in this is contained in this. You can put this in third part, right? So that's it. In this class, what we did is we have defined what is linear combination and a linear span, and then we have solved some three basic problems. And then we have proved that the set of all linear span is a subspace. Then we have defined what is linear sum, and then we have shown linear sum is a subspace. And then we have proved the three parts in this theorem such that V and V naught are subspace of V, and V plus V naught is V, and V intersection contains only the zero function. Okay, so that's it. So if you have any doubt, you will ask. We'll wind off this section. Right? Okay, so thank you. We'll see you in the next class. Right? Thank you.